So this is a lecture of CE on optimal control, and we are going to continue to discuss the problem of linear dynamics with quadratic costs. And we have seen in the previous lecture this result that we could deduce from Pontryaghin's principle. So if you have a linear dynamics x dot equal to ax plus bu, a and b constant matrices, y equals to cx. Now suppose that you have this cost function that means that you want to regulate y, that is to say you want y to be close to 0, and you have a regularization terms on u. So you put a weight, rho is a positive number, and what you are saying is that you want both y and u to be 0, but the relative importance of which one is 0 is measured by this weight, rho. If you increase rho, you are saying that u should be 0, close to 0, and y is free to go. If rho is very small, then u is free to move, and y, if everything is okay, will be driven close to 0. Now, you can reduce this problem to a problem in which you regulate the state that we have seen the solution. And this is simply done by observing that y squared is x transposed, c transposed times cx. Well, this is y transposed, and this is y. Okay, y is a scalar, so you can say that the square of a scalar is the scalar transpose, which is the scalar times itself. So if you apply the results for state regulation with Q, the matrix Q, remember that we had the result when we solved this problem. The solution was a feedback of the state, where the feedback was computed from this expression where P is the positive definite solution of the so-called algebraic Riccati equation. Now you make Q equals to C transpose C, and you get the solution when you replace X transpose QX by Y squared. So the result is this one. When you want to minimize this infinite horizon, don't forget it's an infinite horizon cost, quadratic cost that depends on the output, then the result is state feedback, and the feedback gains are computed according to this formula where P satisfies this so-called algebraic Riccati equation, this particular case. Now, one thing that you can ask is, since you are doing a state feedback, you have some eigenvalues of A, they are the eigenvalues of the closed loop eigenvalues are the eigenvalues of A minus BK. If you replace U there and simplify, then you get X dot equals to A minus BKX. So can we characterize the optimal eigenvalues? And the answer is yes. The answer is yes. And is given by this result called the Chang-Letov theorem. So suppose that you compute, you have a state realization, ABC, and that you compute the equivalent transfer function. So you can compute it in a number of different ways, in particular using these formulas. Remember that the numerator B and the denominator of the transfer function are given by this. We have deduced these formulas using the Laplace transform in the very beginning of this course. Now, you form this polynomial delta of S, which is made of A of S times A of minus S plus 1 of rho. Rho is the weight on the manipulated, rho is the weight on the manipulated variable part of the cost. And times BS, B of minus S. So remember that A and B are the denominator A and the numerator B of the transfer function. Now you form this polynomial, and this polynomial is now of order has now an order which is the double of the order of the original system, because you have A of S times A of minus S. So for instance, if your plant is of second order, delta is a polynomial of order 4, the double. And furthermore, if you have one root of this polynomial, you also have the reflected, you have another root, which is a reflection according to the imaginary axis. That is to say, suppose that S1 is a root, okay? So if S1 is a root, then this means that if you replace S by S1, you get 0, the polynomial delta of S1. Now, consider now that S is equal to minus S1. So compute delta of minus S1. So you go to the definition of delta of S, and you replace S by minus S1, and you get this stuff, okay? But since the multiplication of polynomials is commutative, this last line is exactly delta of S1, the expression for delta S1 that we know is 0. So delta of minus S1 is also 0. This means that whenever you have a root, minus this root is also a root. Okay? So your roots appear in a pattern which is symmetric with respect to the imaginary axis. You can also prove that the optimal controller is asymptotically stable, and you can do that by building a Lyapunov function. Actually, a Lyapunov function, which is, let's go back a little bit, a Lyapunov function which is a quadratic form associated to this P. Okay, so it's a good exercise to show that the closed loop system with this control is asymptotically stable. Okay, maybe we have some time and we do it here, or maybe next week during one of the classes. So another way of solving the problem by pole placement is to build this polynomial, delta S, and to take the stable roots. So the stable roots, I haven't told you that the stable roots are the optimal ones. You always have roots that are either on the left and symmetric on the right. So you always have n stable roots of this polynomial. So you compute these stable roots. If it is a first order problem, it's simple. You get a second order equation. If it is a second order system, then you have a fourth order polynomial. Okay, now you need to solve the roots using a computer or some mechanical computational means. But you can think that you solve it and then take the stable roots. Okay, so it's very simple. Compute the open loop. Compute the open loop transfer function. So that's B over S divided by A over S. Then build this polynomial. Compute the eigenvalues of this polynomial. And take the n roots that are on the left plane. And those are the optimal roots. Now, you can design them a state feedback controller, placing the roots there. And that is equivalent to solving the Riccati equation. Okay? So we have two methods. One method to design optimal controllers based on a quadratic cost for linear plans is solve the Riccati equation, and then compute the gains in this way. Another way, which is an alternative way, is compute the open loop transfer function, compute the polynomial delta of S, compute the roots of this polynomial delta of S, and take the ones that are on the left, semi-plane. And then design a pole placement controller that places the closed loop poles there. And these gains are the optimal ones. So you have these two alternatives. Would you like to make questions? Let me give you an example. Suppose that you have this system of second order. Actually, I will present you two examples, and then I will ask you to do one example in which you do the design by the two ways. So, suppose that you have this state model, state realization, and you want to find out the control law that minimizes this quadratic function with rho equal to 10. Now, you have to compute the transfer function. The transfer function, well, I won't go through all the details, but one possibility is to manipulate the equations. Another possibility is to apply the Laplace transform and solve for y as a function of u, eliminating x1 and x2, or which is equivalent to applying these formulas. Okay, so this is something that you can do in an almost automatic way. So I won't go through the details of computing the transfer function, and the transfer function is this one, minus 1 plus s divided by s squared minus 4. So I put a minus on the numerator. Okay, it's somewhat arbitrary. Now, this is my b of s minus 1 plus s, and this is my a of s, s squared minus 4. So let's form polynomial delta of s, okay, with this a and this b. So a of s, a of minus s is nothing more than s squared minus 4, and then minus s squared is s squared. So I can merely get the power 2 of a of s plus 1 divided by rho, and I know that rho is 10, but I keep it here. Now b of s, which is minus 1 plus s, the minus is missing here because it will disappear, because afterwards I'm going to multiply it by b of minus s, and b of minus s is minus 1 minus s. So both minus cancel. And you can simplify this. 1 plus s times 1 minus s is nothing more than 1 minus s squared. So when you compute the roots of delta of s, you just have to solve this equation with rho equal to 10. Okay. Now you can use a computer, but in this case, you can make a change of variable that amounts to this is a biquadratic equation. This is a biquadratic equation. So if you replace s squared by z, so you get a second order equation, and you get the solutions for z, and then each of these solutions, you have two solutions. Each of these solutions gives origin to two solutions in S, because S is plus or minus the square root of Z. So Z1 equals to 4.6 gives you the origin to 2.14 and minus 2.14. And the same, Z2 equals to 3.5, you get 1.86. If you square 1.87, if you square 1.87, you get more or less 3.5 and minus 1.87. Any question? So you have these four roots. These are the roots of polynomial delta. Two on the left and two on the right. The ones that are the optimal poles that I have encircled here are the ones on the left. Okay? So your optimal closed loop poles will be minus 2.14 and minus 1.87. That is to say, you cannot design a closed loop state feedback system with a desired closed loop polynomial alpha given by this polynomial here, where the roots, of which the roots are minus 2.14 and minus 1.87. Any question? Okay, so we have our plant. We feedback x1 with k1, x2 with k2. Don't forget a minus sign there. And I compute the AK polynomial. This should be an A, not an alpha. Okay. So the characteristic polynomial of the closed loop of this system. Again, I'll let you do that. And then I compare with my desired characteristic polynomial. And immediately I get K1 equals to 4.01 and K2 plus 4 equals to 4. So K1 optimal is 4,01 and K2 is 0. Any question? Okay, let's see another example. Okay, before doing another example, or before proceeding on the slides, let me ask you to solve one problem in two ways. Okay, and the problem is very simple. Let's recall a little bit before I switch to my slides. How did I get these formulas of the Riccati equation? So remember, we did this last class. We have our dynamics, our cost. So our Lagrangian is minus, because I'm minimizing, minus 1/2 x transpose qx plus u transpose ru. The adjoint equation, okay? And the adjoint equation becomes this stuff, because f is ax plus bu, fx is nothing more than a. The terminal condition is not much important here. In the Hamiltonian. And then we minimize the Hamiltonian. We maximize the Hamiltonian, but this corresponds to minimizing the cost, because I have here a minus on the Lagrangian. So I get an expression for u, which is a feedback of the cost state lambda. And so I place my expression for u here in the state model. And then I have also my state equation. Now, I will admit that lambda is minus px. Okay? So I can get rid of lambda here and express everything on x. On the other way, I will differentiate this, so I get lambda dot equals to minus px dot. Lambda dot equals to minus px dot. Now, I'm assuming here that P can change. So when I differentiate Px, there is this term here. But if P is constant, then this is 0. And lambda dot is nothing more than minus Px dot. Okay, so this term here disappears. That's what happens when you have an infinite horizon problem. P dot is 0. It's a constant. Now, I have one expression for lambda dot that involves x, one expression for x dot that involves x. So I put everything in the form of a big polynomial in P times x equal to 0. So for this to be true, this term between square brackets must be 0. Okay? Now, at this moment you are lost. But so let's do one problem and solve this step by step. I will give you some hand. So let's go to the whiteboard. And I have to if you give me 1 minute, I have to install my digitizing table, which I always forget to do. So give me please a minute. Okay. Can you see the whiteboard?
Yes.
Let's change color. And my problem is the dynamics is scalar. Is x and it's open loop unstable. So if u is 0, x will grow as a positive exponential. And my cost is the integral between 0 and infinity of x squared plus u squared. Okay? Now, let's write here when we have x dot equals to f of x u and j equals to psi plus integral between 0 and infinity of L and x and u dt. Then we have minus lambda dot transposed equals to lambda transposed f x plus lx. And I have some condition on the terminal state, but the terminal state that happens at infinity, so that it does not play any role here. And then we have the Hamiltonian equals to lambda transposed f my plus L. And then there is something that we are going to assume, which is that lambda lambda is minus px. Okay, so this is a special assumption. This is what you do in the LQ problem, in your quadratic problem. Okay, so fx lx. Now let's write h, and then h will be okay, we'll see. We will have to maximize it. So please write these things in your notebook, and when you are ready, raise your hand, please, and then we'll proceed. Okay, Vicente, just some more, 1 more minute. So what is f? Who tells me what is f?
X plus u.
X plus u. So fx is
1.
1. L is what?
X square plus u square.
Be careful. You want this is to maximize, max, and here you want to minimize,
So it's minus
minus,
expression, yeah.
minus, okay. So Lx is?
Minus 2x.
Minus 2x. And f? Lambda is a scalar because lambda has a dimension of x. So look here. H is?
Lambda times x plus u minus x square minus u square.
Okay, lambda transpose lambda f plus L, and L is minus x squared plus u squared. Everybody agrees with this? Now, I want to maximize, what type of function is h? What type of function is h as a function of u? So remember, the big trick is that instead of optimizing with respect to entire function u, you take snapshots at general time, you take a snapshot at a general time t, and you maximize h as a function of u. So what type of function is h from u? So it's what? The straight line, the straight line, the sinusoid. It's, I don't know, some funny function. So what is, let's cancel out what is not correct. So it's not a straight line? No, it's not a straight line. Could it be a sinusoid? No. So it's my alter ego. No, it's not my alter ego. So what is the form of the function? Look here. You have h as a function of u. So what type of dependency do you have? Take x as something which is frozen at time t, but u is varying, and you are assuming u to be free. So h as a function of u is what you think?
A quadratic function.
It's a quadratic function. So it's what is the graphic? What is the graphic of a quadratic function? It has a name.
Parabola.
Parabola. Upside down or downside up? How do you see that? You should look at the sign of.
I think it's upside down, right?
Upside down. Why, Alex?
Because it's negative.
The coefficient of u squared is negative. So it's something like this. So you are looking for a point u star for which the derivative is 0. Okay? If you had some constraints, maybe this was not the case, but since you don't have any constraints and you have a parabola, you find the optimum value by which equation? Derivative of h with respect to u is equal to 0. So solve this equation and give me the optimal u. Raise your hand when you found the optimal u.
I have a question.
Mm-hmm.
We don't know the lambda yet, right? And it's also
so you are going to express your result in terms of lambda.
Okay, but then it could be also look different than a quadratic function, right? In the graph.
No, but what you do is you remember the proof we did was we were taking some optimal trajectory for lambda and x, and then we optimize with respect to u. So no matter what happens, this is taken as a constant at each time instant. So the final result for lambda is not, it does not affect the result.
Okay,
and then we know that this stuff here. So if you want to get rid of lambda, you use this expression. Now you have the problem, which is p, okay? But so Alex, tell me.
I think it's lambda divided by 2.
It's lambda divided by 2, probably yes. Lambda of t divided by 2. Because the partial derivative is what? Is is what?
Lambda minus 2y.
Okay. And you equate it to 0 and you get this stuff. Now, if you use this, if you use this expression, then this becomes P divided by 2x. So at each time t, you just do a feedback, and this is the gain. Now, the problem is that you don't know P. Okay? But if you knew P, at least you, at this moment, you know that it is a feedback from the state. Okay? Questions? Okay, so let's try to find P. And the technique is this one. So we differentiate, we know that lambda is equal to minus px. So we differentiate lambda dot is equal to minus px dot, because since the horizon is infinity, p will be constant. Now, the trick is in the end, I want to have some expression on p times x equal to 0. And this implies that this must be 0. So you get an equation for p in this way. Now, I want to get rid of lambda. I want to get rid of lambda dot and x dot. I want to express everything on x. So how can I get rid of x dot, for instance? So this is something which is equals to minus p. Now I want to get rid of x dot. So how can I get rid of x dot? It's written on this whiteboard. You know, there is a game in which you look for something, and the guide is saying cold, 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 warm, very hot. So what do you mean? What you say? Tell me. It's cold, it's warm.
X plus u.
X plus u. Okay, so I like your answer because you say, well, let's stop silly games. X plus u. Okay. But now we have a problem because you made x dot disappear, but there appears u. So where can I get? How can I get rid of u? Remember that u should be the optimal u, and express u.
We derive the optimal value in the lower left side, so it's minus p over 2 times x.
Cancel this u, and I write here this stuff here, minus p divided by 2 x. Okay? Now, what about lambda dot? Where can I go and look for lambda dot? Is there any equation for lambda dot? What about here? No, cold, 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 a little bit warm, warm, oh, very hot. You have the equation for lambda here. So what is the equation for lambda? Let's write it here. Lambda dot. Can I get rid of the transpose?
Yes, because it's scalar.
Yes, okay. So lambda dot minus lambda dot should be what? Lambda. And then the partial derivative of f with respect to x, the Jacobian matrix of f. Where do we have it?
Minus 2x.
No. F, remember, f is your vector field of the differential equation. It's x plus u, so ff is just 1. You agree, Sarah?
Yes, I thought we were already the next part.
Oh, okay. So lambda times fx, which is 1, so you don't place it there, and then lx, and then lx, fx, lambda transpose fx plus lx. Now lx is what? It's here. And this is minus 2x. Okay. Now this means that this is lambda dot is equal to minus lambda minus 2x. But we have this nasty lambda here. How can I get rid of the lambda?
It's minus px.
Okay, so lambda dot is px minus 2x, right? So I replaced lambda by minus px. There was a minus, so it becomes plus. So I place it there. Px minus 2x. Let me see if we don't have any changing in signs that we lost through the way. So there must be some. Oh, this is plus. Sorry. When you cancel this minus, so it becomes minus lambda plus 2x. So plus 2x, and lambda is minus px. I'm sorry. No, it's correct. Minus px plus 2x. No. So this is lambda dot equals to minus lambda plus 2x, and minus lambda is px and 2x. So this becomes px plus 2x. Just copy. There is a minus missing. px plus 2x. Do I have everything correct? I think so. Now, we have to write this in the form of an expression times x. So collect the terms in x. So what you get? You get p plus 2, then plus p minus 1/2 of p squared times x equal to 0. That is to say, you can write it as multiply everything by minus 2, so you get p squared, and then 2p minus 4p minus 4 equal to 0.
I'm not sure you should have a minus sign on the p squared divided by 2, right?
Here,
Yeah, like you move it to
I
the left
multiplied
side.
everything by minus 2.
Oh,
Okay, and I added these two terms. So
okay. Thank you.
I think it's correct now. I think it is correct. So you have the first term on p squared minus 2 times minus 1/2, it's p squared. Then you have 2p times minus 2 minus 4, and then p times minus 2 times minus 2 minus 4. Okay, we get this. And you say that this is true because this equality must be true for any x. Okay, for any x. So the term between the brackets must be 0. So what is p? Solve it. If you compute p, this is our Riccati equation. Okay, so p is equals to you divide by 2, 4 plus or minus the square root of what? 16 plus 16. And p is 2 plus or minus. Now you get 2 squared is 4. You have 2 square root of 2. Okay. Now should we select the plus or the minus? We have two possibilities. We should select p is positive. P is positive. Okay, so p must be equal to 2 plus 2 square root of 2, which is approximately 4.82828. Okay, so your optimal control is divide this by 2 is 1 minus 1 plus square root of 2 x of t. That's the optimal control. Okay? Now, questions? Is it clear? In practice, you know that the form of the algebraic Riccati equation, so you directly write this, and you find p, you had the optimal value, so you replace that value for p. But this was a way of, in a simple case, to go through all the steps. Now, I would like to solve this same problem with Changletov. Before I cancel this out, are you sure you don't want to make any questions? So remember the result, and of course we are going to find the same result. So let's use Changletov. Takes a lot of time canceling all this stuff. So we don't need any of this. Now, remember, for Changletov, we have to find the transfer function. Sorry. We have to find the transfer function b of s divided by a of s. And then we build delta of s, which is a of s, a of minus s plus 1 divided by rho, b of s, b of minus s. And then we find the roots and get the stable ones. Okay? And remember that our j is something which is y squared between 0 and infinity plus rho u squared. So what is the value of rho here in this case, in this problem? Compare your cost function with the general cost function. Well, x is y. In this case, this is a scalar system, so we can take y equal to x. What about rho?
Should be just 1.
Just 1. That's right. Okay, just 1. Now we have to find out the transfer function. How can I find the transfer function or the open loop transfer function? This is open loop. So this is y of s divided by u of s. In this case, y is the same as x. So what shall I do? I apply the Laplace transform to x dot equal to x plus u. So with 0 initial conditions. So what do I get? Laplace transform of x dot. Ooh,
X dot equals S times X.
s times the Laplace transform of x is equal to
2x plus u in Laplace.
so b divided by a is what? Here. So this is the same as
It's
what?
1 over S, I think.
1 over s.
Over S.
Oh, I don't think so. Solve this with respect to x. X is what? Is 1. S minus 1. So this is s minus 1. Okay? Because this is s minus 1x. S minus 1, 1. X equals to u. Okay? So this is pure algebra. Okay, so we have B and A. Now we have delta, right? Tell me what is delta? Delta is what? Vicente, help me. Are you still there? Delta is
Yes.
defined. Delta is defined in this way. So delta is A of S. So what is A of S? You have it here. So
S minus 1
S minus 1
times
times
minus S
minus S minus 1. Okay, so replace A of S and A minus S. So replace simply S by S minus S. Plus, then 1 over O.
1,
1. So I don't write it. B of S,
1,
1. And B of minus S,
1.
1. So this is just 1. Okay? Was it so too difficult? Just a replacement. This is a special case. This is a open loop transfer function. That is to say, the transfer function between u and x without any control. And the numerator is b, the denominator is a. How do you replace there? I haven't proved this that the optimal poles are the stable part of these roots. But you trust in my word. It's the same as Chang and Letov. If you don't trust in China and Russia, what can you trust? Okay, so, and now what shall we do?
Find the roots.
Find the roots. Okay, so let's find the roots of this. Okay, try to find the roots of this. I will do it myself. So you can correct me. So remember that this is minus 1. Okay, now, which root should we select? Which root corresponds to the optimal pole? The positive or the negative one?
The negative.
The negative one, minus square root of 2. Okay, so you have the C-plane. You have one root here. And you have a negative. And this is the optimal one. Okay? But now I want to have a controller. So I assume that my control law is 1. Sorry. I assume that my u of t is minus k x of t. Okay, just to have an idea about the pole, I add some reference here. Okay, now I place it there. So x dot in closed loop. This is x dot equals to x minus kx plus r. So this becomes x dot equals to 1 minus k x plus r. What is the transfer function of this stuff? Here is x equals to r here, 1 and s minus one minus s, 1 minus k, sorry. Am I right? Okay. So my pole is 1 minus k. That's my closed loop characteristic polynomial. Sorry, this is my characteristic polynomial is s minus 1 minus k. So 1 minus k is the optimal, is the pole that I get for a given k. And I want this to be what? Minus square root of 2, which means that k is 1 plus square root of 2, which is the result that we had obtained before. You see? So in this case, what was the technique? We find the optimal poles using Changletov. Changletov means that you form this delta polynomial where A and B are the open loop, B is the numerator and A is the denominator of the open loop transfer function. So this is very simple to compute because you don't need any control. So you get A and B, you replace it there. And you end up with some polynomial, and now find the roots. Find the roots. And you have two roots that are symmetric with respect to the imaginary axis. One is a stable root, the other is an unstable root. So choose the stable root, choose the stable root, minus square root of 2, and then assume that you have a control law, which is a feedback of the state, and place your pole there, which gives you the final gain. Too complicated? No, shouldn't be. Okay, so we stop here today. Any questions? We still have some minutes for questions if you want.